We want to add also the carry forward, which would be a 1 plus a 1, which is a 2. And 2 in decimal is equivalent to the number 10 in binary. So we put down a 0 and we carry our 1. And similarly here we have 0 plus 1 gives us 2. In binary, 2 is the number 10, so we put down a 0 and we carry the 1. Okay. Here we have 1 plus 0 is 1, plus 1 gives us 2. Once again, 2 in binary is the number 10, so we put down a 0 and we carry a 1. Now this is where it gets a little bit tricky. Okay. Well, we have 1 and 1 is 2, and 1 is 3. Okay. That's in decimal, yeah. Okay. But 1 and 1 in binary, okay, 1 and 1 in binary is 10. Okay, so we have a 10. And what we need to add on to that is the 1 that we carried forward. Okay, so when we add that onto this particular addition, what we end up with is 1, 1, 1. Okay, so 1 plus 1 plus 1 is 3, but 3 in binary is the number 1, 1. So we put down a 1 and we carry forward our 1. And you can see here we have a 0 plus a 0 is 0, plus a 1 gives us a 1. No carry forward. 0 plus 0 is 0. 0 plus 0 is 0. So what we're arguing here is that this binary number here, okay, which is the result of adding these two binary numbers together, that this number here should be equivalent to the decimal number 48. And let's just sanity check that. Okay, so let's sanity check that. Let's take this binary number here, 0, 0, 1, 1, 0, 0, 0, 0, and let's convert it into decimal to see do we get 48 as our decimal number. Okay. And don't forget the number systems that we're dealing with are positional number systems, and now that we're dealing with binary numbers, each one of these particular positions represents multiple powers of 2. So this represents units, how many 2 to the zeros there are in the number, how many units, 2 to the zeros 1, how many 1s there is. This represents how many 2 to the 1s, how many 2s. This represents how many 2 squareds, 2 cubes, 2 to the 4s, 2 to the 5s, 2 to the 6s, 2 to the 7s. Yeah. Okay. So that's how many of these we have in this particular number. Okay. Now we can see that we have 0 of them. We have 0 of them. We have 1 of these. We have 1 of these. We have 0 of them, 0 of them, 0 of them, and 0 of these. So actually, the only contributing multiple powers of 2 that we have here is, well, this number is equivalent to, we have 1 2 to the power of 5, and we have 1 2 to the power of 4. Okay. Now 2 to the power of 4 is 2 times 2 times 2 times 2. Okay, let me say that again. It's 2 multiplied by 2 multiplied by 2 multiplied by 2. Let me write it down. 2 to the power of 4 is the same as 2 times 2 times 2 times 2. Well, 2 2s is 4. 2 4s is 8. 2 8s is 16. So 2 to the power of 4 is equivalent to 16. Okay. Now, what's 2 to the power of 5? Well, it's 2 to the power of 4 times 2, okay, which is the equivalent to 32. Okay, so what we end up with is that this binary number here, along here, is equivalent to 32 plus 16, which is equal to 48 in base 10, as required. Okay. So I know this was a very, very long way around doing binary addition. Okay, what we did first was we just took two decimal numbers in base 10. We added them together so we know what the sum of them is going to be in base 10. And what we then did was we converted 27 and 21 into their binary representations, okay, to give us two new numbers. This number here representing the number 27, this number here representing the number 21. We know the sum of them should be 48 in decimal. But in binary, when we sum them together, we get this binary string here. Okay. Now the question that we have now is whether this binary string is equivalent to 48. And as I mentioned, each one of these digits, okay, in this binary number, okay, tells us how many multiple powers of 2 we have in this positional system. Okay, and all we have is we have 1 2 to the 5, 1 times 2 to the 5, and plus we have 1 times 2 to the 4. 2 to the 5 is 32. 32 times 1 is 32. 2 to the 4 is 16. 1 times 2 to the 4, which is 1 times 16 is 16. 32 plus 16 gives us 48. So that was just our sanity checking. We could also take 48 and we could convert it into binary by doing successive divisions by 2, keeping track of the remainders. And what we would notice is that this string here, okay, of remainders would be equivalent to this particular string here. Okay. One other thing just to keep in mind is that there's a number of cases that we could have when we're adding digits to digits. Okay, we could add a 0 with a 0 in binary. Okay, well, a 0 with a 0 in binary is just 0. We could add a 0 with a 1. Okay, well, a 0 with a 1 in binary is just 1. We could add a 1 with a 1 in binary. Well, a 1 and a 1 in decimal would be 2, and 2 represented as binary is the number 10. Okay, and then the worst case scenario that we could have is where we, well, not the worst case, we could have a carry forward, like in this situation here where we carry forward a 1, in which case we have a 1 plus a 1 plus a 1. There's 3 1s being added together here. In decimal, that's the number 3, which is equivalent to 1, 1. But I suppose in binary what we have is we have the 1 plus the 1 gives us 1, 0, and we need to add on the carry forward. And when we add them in binary, 1 and 0 is 1. And we have a 0 here, so we have no carry forward, so we have a 1 and a 0 is a 1, so it's the binary number 1, 1. And that's why we put down our 1 here and we carried forward our 1. Okay, guys, that was just one particular example of taking 2 decimal numbers, converting them into binary, adding the resulting binary numbers together, and just, I suppose, sanity checking to make sure that this binary number actually is equivalent to what we would expect when we add the 2 decimal numbers together. Okay? So once again, this was Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland, and I hope this short video was somewhat helpful.